Look, everyone knows the numbers. 100 red billion galaxies, and in each galaxy, roughly 100 red billion stars. Wherever you look, there are planets. So people sit back and quickly say, obviously, there must be someone else out there. Curious. With so many opportunities, with so many cosmic rolls of the dice, the idea that we are alone sounds crazy. Surely there must be someone out there, maybe millions, maybe billions of civilizations scattered across this vast sky, talking to each other, building things, and perhaps just like us, wondering if someone out there is watching them. That is the conclusion that feels the most natural to human beings, the most reasonable, the most intuitive size. But I believe that conclusion is completely wrong. Not because I enjoy saying it and not because I like making people uncomfortable, but because one day I sat down quietly with a pencil and a piece of paper and I actually started doing the arithmetic. And when you do the arithmetic honestly, when you refuse to let hope and wishful thinking quietly sneak into the result, you eventually find yourself in a very cold, very quiet room. And in that room, you are alone. I've spent a long time thinking about this. I've talked to biologists, astronomers, chemists, engineers, all kinds of people, and most of them begin from the same place. They say, Richard, the numbers are too big. You can't fight the numbers. And I reply, why not? I can, because the numbers on the other side of the equation are big too. But the problem is nobody wants to look at those numbers. Now, let me make something very clear. I'm not talking about bacteria. I'm not talking about some slime frozen on a rock beneath the ice of a distant moon. Maybe that exists. Maybe it really does. Because frankly, chemistry likes to make complicated molecules. And sometimes those complicated molecules start doing interesting things. Fine, that's possible. But that's not what I'm talking about. I'm talking about something that can look up at the sky and feel wonder. I'm talking about a creature that can build things, a radio telescope, something that can ask the very question we're asking right now. That kind of life, intelligence, consciousness, technology, whatever you want to call it. And the reason most people believe it must exist somewhere else is simple. They look at the size of the universe and they cannot imagine all of that space being empty. It feels wasteful, it feels wrong. Surely, they say, surely nature wouldn't build something this vast for just one audience. Now, let me walk you through the logic, because at first the logic sounds wonderful. It really does. Start with our own galaxy, the Milky Way, roughly 200 billion stars. And from observations made by missions like Kepler Space Telescope, astronomers have learned something remarkable. Most stars have planets, not a small fraction. Most of them. The average star seems to have at least one planet, and many have several, which means that in our galaxy alone, you're looking at hundreds of billions of planets. Some estimates go even higher, perhaps 1 trillion if you include all the smaller worlds. Out of those, a meaningful fraction sit in what astronomers call the habitable zone. Not too close to the star, not too far, just the range where liquid water might exist on a planet's surface. Now, that range depends on the type of star and the kind of atmosphere the planet has, so it's fuzzy. But even conservative estimates suggest tens of billions of potentially habitable planets in this single galaxy. And by the way, habitable zone is a terrible name. It should really be called the liquid water zone, because that's all it actually means. It does not mean there are parks. It does not mean oceans and forests. It simply means the temperature might allow water to stay liquid. That's it. Mars sits in the habitable zone. And Mars is not exactly a pleasant place to live. Venus was once close to the habitable zone as well, and Venus has a surface temperature of about 860 degrees Fahrenheit with clouds that rain sulfuric acid. Habitable technically maybe, but when people hear habitable zone, they imagine forests, oceans, civilizations sitting around having coffee. That is a very long way from temperature allows liquid water, a very long way. Still, even with that correction, we're talking about tens of billions of possible worlds in one galaxy. And there are hundreds of billions of galaxies in the observable universe. Multiply those numbers together, and you get something so enormous, it almost stops meaning anything. Something like 1022 or 1023 potentially habitable planets across the observable universe. That's roughly 10,000 billion worlds. People see a number like that and they say, case closed. There's no way we're alone. The math won't allow it. Allow. And I understand that reaction. If someone told me there were 10,000 billion lottery tickets and only one of them was a winner, I'd bet everything I owned that someone was holding it. The numbers are just too large. But this is where the trouble begins. Because having a habitable planet is not the same thing as having life. And having life is not the same thing as having intelligence. And having intelligence is not the same thing as having technology. And having technology is not the same thing as having technology right now at the exact moment we happen to be looking. Every one of those steps is a filter, and we have absolutely no idea how fine those filters are. That is the part people skip. They get excited about the giant number at the top and forget to ask the crucial question, What do we have to divide it by? There's a famous way of organizing this problem. In 1961, astronomer Frank Drake wrote down what's known as the Drake equation. It isn't really an equation in the strict physics sense. It's more like a way of organizing our ignorance. You start with the rate at which stars form, then multiply by the fraction of stars that have planets. Multiply by the number of habitable planets per star system. Then multiply by the fraction of those planets where life actually appears. Multiply again by the fraction where life becomes intelligent. Multiply again by the fraction that develops communication technology. And finally, multiply by the average lifetime of such a civilization. It's a beautiful structure, but the data is terrible because the first few terms we can estimate reasonably well. Stars form at maybe a few per year in our galaxy. Most stars have planets. Perhaps 20% have something in the habitable zone. Fine. But the next steps, the crucial ones, we know almost nothing about. Does life arise easily? Does intelligence emerge often? Do technological civilizations survive long? We have no idea, none. We're guessing. And depending on the guesses you make, the answer can range from millions of civilizations in our galaxy to less than one. The equation doesn't give you the answer. It tells you how much we don't know. And what we don't know is almost everything. The last term is especially brutal. The average lifetime of a technological civilization. How long does a species keep its radios on? 1,000 years, 10,000, a million? If that lifetime is short, if civilizations usually destroy themselves after only a few centuries, then even if millions of civilizations have existed across cosmic history, almost none would exist at the same time. They would be like ships passing in the night, except the night lasts 13 billion years and the ships are lit for only an instant. Now consider the very first step, going from a lifeless planet with the right conditions to actual life, simple single-celled life. How difficult is that? We know what happened here. And it seems to have happened fairly quickly, geologically speaking. Within a few 100 million years, after Earth cooled enough to support liquid water, something was already alive. That makes some people think the process must be easy. Chemistry plus water plus energy plus time equals life. A simple recipe. But we only have one example, just one. And that example is biased because if life had not appeared here, we wouldn't be here asking the question. You cannot draw statistical conclusions from a sample size of one, especially when the sample itself exists only because the outcome succeeded. That isn't science. That's a card trick. For all we know, the origin of life might require such an unlikely chemical accident that it happens only once in every 10, 20 planets. If that were true, then even with all those habitable worlds, life might arise in the observable universe only once. And that once could be us. I'm not saying that is the number. I'm saying we don't know the number, and that is the crucial point. People assume the probability must be high because it feels like it should be high because life appeared quickly here. But feeling is not calculating. Let me give you an analogy. Imagine you're dealt 5 cards in a game of poker and they form a royal flush. You might say, wow, that happened on the very first deal. It must be easy to get a royal flush. But you would be wrong. The probability of a royal flush is about 1 in 650,000. You just happen to get lucky. If you insisted that royal flushes must be common simply because you saw one immediately, you would lose a lot of money at poker. That's essentially what we're doing with the origin of life. We saw it happen once on the only planet we've studied in detail, and we declared that it must be easy. But we've only looked at one hand, a sample of one. And here is something that really bothers me. People often say, well, we found amino acids and meteorites, and we've detected organic molecules and interstellar clouds, so the building blocks of life are everywhere. And that part is true. The building blocks are everywhere. But having building blocks is not the same thing as having a building. I could have a pile of bricks sitting in my backyard. That doesn't mean I have a cathedral. The gap between amino acids floating in space and a fully functioning, self-replicating cell is not a small gap. It's a chasm, a gap so enormous that no one has managed to bridge it in a laboratory, even after decades of research. As of today, we still cannot create life from scratch. We don't even fully understand how it happened the first time. But let's suppose I'm wrong about that. Let's suppose life really does appear easily on many planets. Fine, give me that assumption. Let's say 1/4 of all habitable planets develop simple life. That would still mean billions and billions of living worlds, as Carl Schorn liked to say. Now we hit the second filter, and this one is brutal. Life existed on Earth for roughly 3.5 billion years before anything resembling intelligence appeared. 3.5 billion years. Think about that. For most of Earth's biological history, the most advanced organisms were single cells. Eventually, multicellular life appeared. Then it took another billion years before anything developed a brain worth mentioning, then hundreds of millions more years before creatures were building tools and asking questions about physics. So here's the real question. Was that progression inevitable once simple life exists? Is intelligence guaranteed to appear eventually, or was it a cosmic accident, a chain of unbelievably unlikely events, a sequence of accidents that just happened to line up on this one particular planet? And the uncomfortable truth is that the evidence, at least what little we have, leans toward the accident theory. Look at what had to happen. First, you needed a very specific kind of cell, the eukaryotic cell. As far as we can tell, that kind of cell arose from an event that appears to have happened exactly once in the entire history of life on Earth. One bacterium swallowed another, and instead of digesting it, the two formed a partnership. The swallowed one eventually became the mitochondrion. That event, so far as we know, happened once in 4 billion years. Not twice, not 100 times once. Without that event, you don't get complex cells. Without complex cells, you don't get multicellular organisms. Without multicellular organisms, you don't get brains. And without brains, well, you can see where this leads, and that's just one bottleneck. There were others. The evolution of sexual reproduction, the mysterious burst of biological diversity known as the Cambrian explosion, the development of eyes, the emergence of nervous systems complex enough to support abstract thought. Each of these steps may have been extraordinarily improbable. Now think about intelligence itself. Evolution does not aim for intelligence. Evolution has no aim at all. It simply produces whatever organisms manage to survive and reproduce. By that measure, beetles are far more successful than humans if you count the number of species, and bacteria are more successful than both of us. Intelligence is expensive. A large brain consumes enormous amounts of energy. About 20% of the energy your body uses goes to your brain. Even though the brain makes up only about 2% of your body weight, for most organisms in most environments, that is a terrible trade-off. You would often be better off growing thicker armor, running faster, or producing more offspring. Intelligence only becomes useful under very specific ecological pressures. Change a dozen details in the geology and climate of Africa over the past few million years, and there is no particular reason to think that large-brained primates would ever have appeared. Remember this, dinosaurs ruled Earth for more than 160 million years, and during all that time, they never developed anything resembling our kind of intelligence, not once. If intelligence were an easy evolutionary destination, the dinosaurs should have reached it long before we did. The fact that they didn't tells you something important. Intelligence is not the default outcome of evolution. It is a fluke, a wildly improbable fluke, dependent on chains of contingent events stretching back billions of years. So the chain might look something like this. Start with a habitable planet. Step 1, the origin of life. Step 2, complex cells. Step 3, multicellular life. Step 4, nervous systems. Step 5, intelligence. Step 6, tool use and technology. Step 7, technology capable of communication across space. Step 8, that technology existing at the same time someone else is listening. If any one of those steps has a probability of 1 in a billion, your giant cosmic numbers vanish. If 2 or 3 of those steps are 1 in a billion events, the expected number of technological civilizations in the observable universe falls below 1, which means we might simply be the lucky winners or perhaps be the only entrants. Now, someone in the back might object, Feynman, you're just inventing probabilities. You're guessing. And that's absolutely true. I am guessing. But the people who insist the universe must be full of life are guessing too. The difference is that I'm being honest about the uncertainty. They tend to sweep it under the rug. Let me put the question differently. The real issue isn't whether the universe is big enough to produce intelligence. Of course it is. The real question is whether we have any evidence that intelligence arises easily. And the answer is simple. We do not. We have exactly one example. And that one example took 4 billion years, required several events that appear to have happened only once, and produced a technological species that has existed for only a few thousand years out of a planetary history of 4.5 billion. A blink, a spark. We may be the exception that barely happened. But suppose, just suppose, there is another civilization out there somewhere. Even then, the physics of detecting them, reaching them, or being reached by them is brutally difficult. Consider the nearest star to our sun, Proxima Centauri. It's just over 4 light years away. That sounds close, doesn't it? Closest star in the sky. But think about what 4 light years really means. Light travels about 186,000 ms. In a single year, that's roughly 5.9 trillion miles. Multiply that by 4, and the distance to the nearest star is about 25 trillion miles. Now compare that to the fastest spacecraft humans have ever launched. Even the fastest probes travel only tens of thousands of miles per hour. At that speed, reaching Proxima Centauri would take around 75,000 years. That's not a mission, that's a geological epoch. The last ice age ended about 12,000 years ago. We're talking about travel times 6 times longer than all of recorded human civilization, and that's the closest star. Most stars in the Milky Way are thousands of light years away. Our galaxy itself is roughly 100,000 light years across. The nearest large galaxy, Andromeda Galaxy, sits more than 2 million light years away. Beyond that lie billions of galaxies stretching billions of light years in every direction. So you want to visit them? Then we must talk about energy. To accelerate even a small spacecraft to 10% of the speed of light requires energy comparable to hundreds of nuclear explosions. And that still gives you only 10% of light speed. At that velocity, the trip to Proxima Centauri would still take over 40 years one way. And that's before you even consider the brutal mathematics of the Tsiolkovsky rocket equation. The rocket equation is merciless. It doesn't care about clever engineering. It doesn't care about optimism. It's a mathematical law. The faster you want to go, the more fuel you need. And the required fuel increases exponentially. To reach another star within a human lifetime would require propulsion systems and energy sources that may lie far beyond anything realistically imaginable. And space itself is not empty. At 10% of light speed, even a grain of sand would strike your spacecraft with the energy of a bomb. Interstellar dust, hydrogen atoms, tiny particles scattered through space would become a constant storm of high-energy impacts. You'd need heavy shielding. More shielding means more mass means more fuel, and once again, the rocket equation wins. Some researchers suggest alternatives like laser-driven light sails. A beautiful idea, but even those proposals would require laser systems producing hundreds of billions of watts, focused onto a sail accelerating away at incredible speeds. Possible in principle, perhaps likely in practice, I'm not so sure. And even if you solved all those problems, you would still face the challenge of sending information back across light years of space. Signals weaken according to the inverse square law. The farther a signal travels, the more it spreads. At interstellar distances, a radio transmission becomes fainter than a candle seen from across the planet, much fainter, which is why projects like SETI spend decades listening for even the faintest whisper from the stars. But there is an even deeper problem, not distance, time. The universe is about 13.8 billion years old. Human technological civilization with radio transmitters has existed for roughly 200 years. 200 years out of billions. That's not a window, that's a crack. For another civilization to communicate with us, their technological window would have to overlap with ours. And if their window is also only a few centuries wide, the chances of overlap become vanishingly small. This was the essence of the puzzle posed by Enrio Fermi. If intelligent civilizations are common, where is everybody? The sky is silent. Our solar system shows no signs of alien probes, no megastructures, no interstellar engineering, just rocks, ice, gas, radiation, and silence.